You know, it's easy to think of our planet as this solid, permanent rock beneath our feet. But the truth is, it's a dynamic, powerful, and sometimes incredibly violent engine. Today, we're going to explore the colossal forces that are constantly shaping our world, from building entire mountain ranges to unleashing just unimaginable destruction. And we're going to start with a single, devastating event.
Just take a look at this. This is what was left of a neighborhood in Banda Aceh, Indonesia. You can see how the landscape was just scraped clean, right down to its foundations. And yet somehow, one single building is left standing. It's an almost surreal image, and it's a testament to the sheer, raw power of what happened here.
And when you pull back, the true scale of the devastation becomes, well, it's just staggering. This wasn't one neighborhood. We're talking about an entire coastline, home to thousands and thousands of people, completely erased from the map in just a matter of minutes.
So it really makes you wonder, right? What kind of force, what power of nature can actually do this, to wash away entire communities and literally reshape the land they were built on? That's the question we're here to answer.
Well, what you were just looking at was the aftermath of the 2004 Indian Ocean earthquake and tsunami. It's one of the deadliest natural disasters in all of recorded history.
This map really shows you the sheer scale of it all. See, the earthquake itself happened right off the coast of Sumatra. But the energy it unleashed? Oh, it didn't stay there. It sent massive waves rocketing across the entire Indian Ocean, causing death and destruction in 14 different countries, some of them thousands of kilometers away from the epicenter.
And the human cost, well, it was just unbelievable. More than 225,000 people were killed or simply went missing. That's a tragedy on a global scale. 250,000 lives just gone because of a single geologic event.
So how does something like this even happen? Well, it starts when a massive undersea earthquake violently shoves a huge section of the seafloor up. All of that movement displaces a colossal column of water right above it. Now, out in the deep ocean, these waves are moving at the speed of a jetliner, but they might only be a few feet high. Ships can pass right over them and not even notice. But as they get closer to shore, into shallower water, they start to slow down, and all that incredible energy has nowhere to go but up, piling the water into an immense, unstoppable wall of destruction.
But, you know, a tsunami is really just the effect. It's not the root cause. To really get what's going on, we need to look deeper at the constant, powerful stresses that are always at work on our planet's crust.
And it basically boils down to three main forces that are deforming the Earth's crust. You've got compression, which is a squeezing force, you've got tension, which pulls things apart, and shear, which is a kind of sliding or grinding force. These three are the real engines of geologic change.
Let's focus on compression for a second. Okay, imagine you're pushing the two ends of a rug together. What happens? The rug has nowhere to go but up, right? It buckles and folds right in the middle. Well, the Earth's crust reacts in a very similar way when it gets squeezed from opposite sides.
And this is the incredible result. That exact same buckling force, when you apply it to the Earth's crust over millions and millions of years, can actually fold solid rock. This is how entire mountain ranges, just like the Appalachians you see here, are born.
Now, all of this squeezing, stretching, and sliding creates weak spots in the crust, and those weaknesses allow molten rock from deep within the Earth, magma, to find its way to the surface. And that leads to one of nature's most spectacular and fiery displays, volcanoes.
So, why do some volcanoes have these gentle lava flows while others just explode violently? Well, to understand that, you need to understand one key property of their magma, its viscosity. And really, all viscosity means is how thick or runny a fluid is. It really all comes down to this. If the magma has low viscosity, so it's runny, kind of like water, gas bubbles can escape really easily, and that leads to those quieter lava flows. But if the magma has high viscosity, meaning it's thick and sticky like honey, it traps all that gas. Immense pressure builds and builds until finally you get a catastrophic, explosive eruption.
But volcanoes aren't the only thing that happens when these tectonic stresses build up. When that pressure becomes too much and the rock doesn't just bend, but it actually snaps, the result is an earthquake.
Okay, so here's the key idea. You have stress building up in the Earth's crust, sometimes for decades or even centuries. When that pressure finally gets to be more than the rock can handle, it breaks.
That sudden slip along a fault line releases all of that stored up energy in an instant, sending out seismic waves that we feel as an earthquake.
And the thing is, these earthquakes don't just happen anywhere. They happen in very specific zones all around the globe. You'll find them mostly along the boundaries where tectonic plates are colliding, pulling apart, or sliding past one another. You can literally trace these belts along coastlines and through these long chains of islands.
So we've seen the immense, unstoppable power of our planet. And these forces, we can't stop them. But that doesn't mean we're completely helpless. The impact these events have on us often comes down to one single thing: preparation.
To really show you what I mean, let's look at a tale of two earthquakes. They happened in the same year. They had nearly identical strength, but their stories could not be more different. Okay, first, in January 2010, a magnitude 7.0 earthquake strikes Haiti. Buildings were poorly constructed, and they just collapsed, leading to an estimated 200,000 deaths. It was a catastrophe. Then just 8 months later, a slightly stronger magnitude 7.1 earthquake hits New Zealand. The outcome there? 0 deaths. The critical difference wasn't the earthquake itself, it was engineering. It was strictly enforced building codes designed to withstand exactly that kind of shaking.
And that right there drives home such a powerful point. In these active zones, the ground is always going to shake. The biggest threat isn't the planet itself, it's the failure of the things we build on top of it. Our own preparedness is what separates a scary event from an absolute disaster.
Which leaves us with this one final thought. We live on a dynamic, restless planet. We cannot stop the Earth from moving. So the real question we have to ask ourselves is, how can we learn to live with it? How can we better prepare our world for the next time it does?